Well, I'm going to show you here a little trick using Gauss's law to figure out how electric charge distributes itself when we put it on a conductor. But I'm going to start with a real standard kind of situation where we have a metal ball like this with some net charge on it. And I usually, well, maybe we can start with some negative charge in this case. Maybe we'll put a negative 5Q on there. We put everything in terms of Q. And then we surround that metal ball with a shell, a hollow shell. So the ball is going to be in the cavity of the shell. And we're going to put a net charge on that as well. We can put anything we want to on here. Maybe I'll put a positive 3. And our question is, where does that charge reside? Now, I know my drawing's a little off here. Everything should be nice and concentric. And even though I've written the charges in specific spots there, I'm trying to figure out where those charges are going to reside. So I want to show you the use of Gauss's law for this. So the first step is, anytime we use Gauss's law, to draw a Gaussian surface. So I'm going to first draw a Gaussian surface on the very inside of the ball. And I'm not going to write anything here, but I'm going to talk through how we use Gauss's law. The first thing you have to know, and this is just a premise anytime you work with conductors, is we cannot have an electric field inside of a conductor. Because if there were an electric field inside of a conductor, then we would have those free electrons that are in metals just moving all over the place, following those electric fields. So we start with the premise that there's no electric field. And what that means in this case is, because there's no field at any point on that Gaussian sphere, then we cannot have any electric flux piercing that Gaussian sphere. Because remember, flux is found by adding up the strength of a field at a particular point on a surface times that little piece of area at that location where you measure the field. And then you do that all over the entire surface and add up all the numbers that you get. Well, I'm just going to get 0 for every E number, so that's going to add up to a big fat 0. So that tells me is I can't have any flux through there, and if Gauss's law says that the flux is proportional to the amount of charge that I put inside the Gaussian sphere, that means that there's no charge inside the Gaussian sphere. So where's the only place that it could reside? That is on the surface, the outer surface. So if we could see these negative 5 Qs of charge, extra electrons, they would almost like be painted on the outer surface of that, a coating. So that explains where they are on the ball. Now let's do a similar kind of thing for the shell. The shell, I'm going to draw a Gaussian surface inside like this. Now again, I'm inside the metal deliberately. And for the same kind of argument, I'm going to say I have no electric flux through there since I'm in the metal and I can't have any field. And that means I cannot have any net charge inside that sphere that I just drew. And you're going to say, well, wait a minute, I see minus 5 Qs inside there. That's true. That tells me there must be positive 5Q somewhere else inside there to make a net of 0. And indeed, if we could see it, almost like it's painted on the inner surface of this shell, is minus 5Q. I'm sorry, that's plus 5Q. Plus 5. Red usually denotes positives, at least when I draw it. So that explains where some of the charge is. And you're going to say, well, wait a minute, how did we put positive 5Qs on an inner surface when we only had positive 3Q as a net charge to begin with? What that tells us is we must have sent 2 Q's worth of negative charge away from that inner surface to make a total of 5. So again, I'll say that again. The extra net charge that we put on there, the plus 3, we could think of that being on the inner surface, but the remaining 2 that we need must have come from the original charges on the conductor itself, and that only happens if we move 2 Q's worth of charge away. I think we established earlier that we cannot move charge to the interior of the metal. I mean, on the actual chunk of metal itself. It can only be on surfaces. So what that means is we have -2 that we could see coating the outer surface of the outer shell. So all of that there, a total of -2Q. So I think what I'm going to do here is I'm going to erase the original net charge of +3, and now we can really see what we had is a net of +3 on the shell and a net of -5 on the ball, and that is how the charge has distributed itself. It's not too bad to think of this as, you know, the -5Q in the middle wanting to attract the opposite charge. How much charge would it want to attract? Well, it turns out it attracts exactly as much charge, just of the opposite sign. And that's why we have the same amount of charge, just opposite kinds of charge on the two surfaces that are closest to each other. And then what's interesting about this too is what we could see from the outside if we were just, let's say, out here, standing here, looking at the sphere. What we would see coating the outer surface is the total net charge that was put on any part of the system at all. So a total of -5 and +3 is a net of -2. So that would be visible to somebody standing on the outside looking in. So I think we're going to call it quits there. This is, of course, explained pretty well in most standard textbooks, including Dr. Knight's book that we use. Hopefully this has helped maybe to clarify a few things if you needed it.